Alright, so at this stage we already know that rate of change of magnetic flux can give rise to EMF, right? And it is called induced EMF, and the expression for that induced EMF is given by Faraday's law, which is basically given by this expression, that EMF E is equal to d phi subscript B, that B is only for indicating that it's magnetic field, so d phi B divided by dt. The rate of change of magnetic flux basically is equal to induced EMF. So rate of change of magnetic flux is induced EMF, right? So actually the law says it is proportional to the magnetic flux, but later on turns out that the proportionality constant is 1. So now we can write the rate of change of magnetic flux is equal to the induced EMF, to induced EMF. Great, right? And the negative sign basically tells us the direction of induced EMF. And that negative sign is actually according to the Lenz's law, right? The negative sign was coined because of the Lenz law, which actually gives the direction of induced EMF, and it goes something like this. That I'll try to write it in the shortest way possible. So Lenz's law basically says this, that the induced EMF is such that the induced EMF is such that it basically opposes its own creator. I'll write it like that. Its creator. And who is this creator over here? The changing magnetic flux, right? So changing magnetic flux induced the EMF, and that induced EMF will be in such a direction that it opposes its own very creator, that is the changing magnetic flux. So basically, to sum this statement up, if the magnetic flux happens to be increasing, then the induced EMF will try to reduce it, and if the magnetic flux is, say, decreasing, then the induced EMF will try to increase. And these are the things that we already know. Coming into this video, we already know these things, right? Yeah, what we'll be actually learning in this video is basically this right here, motional EMF, right? This is one of the ways in which you can induce EMF, right? Let's try that. So basically, let's say we have a shape like this, something like this. We have, let's say, a wire which is bent in this particular shape. I have taken a long wire and we have bent it in this shape, right? Some sort of U sort of shape. And then near this wire we have one more conducting rod of sorts, which can basically slide over this U-shaped wire. So I have this rod, and this red color rod you're seeing right now is also a conductor, which can basically slide over. These are like tiny rings which will help the rod slide over here, like left and right. This length right here, this length is x, the distance of the snapshot. Let's say this rod basically can slide, but let's say when we were doing this particular thing, the motional EMF experiment, right now the rod was at a distance of x from this end. Let's name this end, maybe, I don't know, let's say this end is AB. So basically the CD end is at a distance of x from the AD end, and this can move basically. We'll see about that. Also, the length of the rod which you are going to slide sooner or later is L. So length of that rod is, say, L. Alright. Apart from this, the region that you see here has a magnetic field directed like this. You can also have magnetic field with a bunch of dots. Basically this, you already know that this means that the magnetic field is going inside. So yeah, so all over this region you have magnetic field in this direction. Magnetic field is going inside, And then let's try to name these variables. So magnetic field, basically, that you have magnetic field, let's say that field is, obviously the direction is inside with the crosses, is, let's say the strength is B Tesla. So magnetic field is B, and you have a slidable rod whose length is L, and that rod is at a distance of X, yeah, and all these things. And now that I'm saying that this you can slide, so let's say I'm going to try and slide this rod maybe in this direction. Maybe we'll try to slide this rod in this direction, and let's say we're doing that with some velocity v. Okay, so the velocity with which we are sliding the rod, so velocity of the rod or speed of the rod with which you are sliding the rod is let's say v. All right, and looks like we are right now, you can move it rightwards also, but we seem to be moving it in left direction. So yeah, okay, fine. So this is the situation right now. But as the name suggests, motional EMF, that means the motion of this rod should give rise to EMF, right? So let's see how that works, and then finally we'll try to get the expression also. Now, does this situation, and we are done with the description of the setup. This is basically the entire setup you will be needing to study motional EMF. Now the basic question is, do we have everything we need to have in order to get induced EMF? Let's see what all we need to get induced EMF. We need this thing. What do we need? We need, and we've seen this already in previous videos, that we need a changing magnetic flux. We need a changing magnetic flux, and if you have changing magnetic flux with respect to time, then that itself is going to give you EMF. So in order to have induced EMF, you need to have a changing flux. Let's see if you have a changing flux over here. Let me try to write the expression for flux in this region. So let's try to write the flux in the region of ABCD. So look at the loop ABCD here. Loop ABCD, yeah, looks like some magnetic field lines are definitely crossing through the loop ABCD, right? CD being the rod, but still ABCD is still a closed loop, right? Through that, all this region, let me try to, so yeah, basically this region, there is definitely magnetic field lines passing through this region, and therefore definitely there is flux. Let's say at this very instance, when I took this snapshot of the image, the rod is actually sliding, but let's say during this motion I took the snapshot at this very instance where the distance of CD from AB happened to be X. At this instance, if I want to find the flux, what is the definition of flux? Definition of flux basically is this. It is magnetic field into the area into cos of angle between the field vector and the area vector, right? So let's try to get that expression for flux. In this case, magnetic field, as already suggested here, is B, so magnetic field is going to be B, and area is going to be this entire area, this area right here, and that area seems to be the area of a rectangle, which basically is length into breadth, which is X into L. So I'll just write the area as L into X. All right, into cos theta. Now let's focus on the cos theta, right? If you somehow can get the value of theta, then you can easily get the value of cos theta. I'm thinking theta over here is 0. Let's see why. Theta is basically angle between, let me just mention that first. Theta is angle between the area vector and the field vector, magnetic field vector basically, right? So area vector and field vector, the angle between them. What's the direction of magnetic field? Going inside the screen, right? It's perpendicular. The crosses basically mean that the magnetic field is perpendicular to the screen and going inside. All right, and you know this, that the area is always perpendicular to the surface itself. So ABCD surface seems to be lying on the plane of this screen, right? So the perpendicular that you will be drawing to this screen will be inside the screen, okay, or outside, but in this case let's say it is inside. And with that, I think the angle theta turns out to be 0 degree, right? Because magnetic field is inside, area vector is also directed inside, so angle is going to be 0, and we know this, that cos 0 is 1. So I'm thinking, because cos 0 is 1, I can simply write cos theta or cos 0 is 1. So I don't really have to worry about the cos theta anymore. It's like b into area into 1, which is like nothing, right? Alright, now that we've got the expression for flux, now the question to you once again I'm asking is this, that is this flux, this magnetic flux expression that you're writing, that we have written, b into lx cos theta anyway is 1, is this flux changing with respect to time is the question. If the flux is changing, then definitely you'll have EMF. If it is not changing, then you'll not have EMF, right? So the question is if the flux is changing, and I think the flux is changing because see, this red color rod is going to slide leftward with some velocity. Even if with velocity or not, it is definitely changing, right? The rod is sliding. With the rod being slided over here, I'm thinking the area is definitely going to decrease, because at one instance this distance is x, and as the rod starts sliding towards left, as this rod slides towards left, and maybe at a later stage the rod will be, I don't know, after a while will be somewhere here, right? And definitely x will be less than what it is right now, and then the area you'll be worried about is only this region, and this much of region will be waste. It'll not be part of your flux. So definitely flux is decreasing. Yeah, and we know that increasing or decreasing change is change, right? So definitely flux is changing. Now that you know that flux is changing, the only thing you are going to have to do is use Faraday's law to get the expression for EMF. How do we use it? So basically you have to only find the rate of change of flux. Once you can somehow get your hands on rate of change of flux, that itself is going to be your EMF, right? So yeah, you got the expression for flux. Now we'll just be using Faraday's law, right? So according to Faraday's law of EMF, of EMI, electromagnetic induction, according to Faraday's law, we know this, that induced EMF E is minus of d phi b, that is rate of change of magnetic flux with respect to time, is induced EMF, right? So let's just substitute the value of phi in this expression. I'll just write the remaining part, d by dt L, right? And we'll wait for phi. This phi, actually maybe I can write it as phi or phi b, it's the same thing, because now that we definitely know for sure that we are not talking about electric flux. So sometimes I'll be using just phi instead of phi b, right? Yeah, so phi looks like it is blx, so I'm going to use the expression for flux over here. So flux is I'll just write it in a bracket. So b into L into x is your magnetic flux, and you're going to differentiate with respect to time. So induced EMF E is equal to minus of, now let's look at these three terms. You have B, you have L, and you have X. Among these three terms, the magnetic field, is magnetic field changing with respect to time? Let's focus on the diagram for a bit now. As the time moves, as time goes ahead, the rod is sliding leftwards. It's going to slide even further and further to the left towards AB. The CD is going to slide towards AB. Okay, but with that, is the magnetic field strength changing from B to something else? Is the magnetic field decreasing? I don't think so. Is the magnetic field increasing? No, sir. Right? So magnetic field is not changing. So B is constant. So there's no point in differentiating B. According to chain rule, it will remain a constant. So magnetic field will remain constant. Is length of the rod changing? Length is this length right here. This is the length of the rod. This much is the length of the rod, right? As the rod slides with the time towards left, does the length change? No. X changes, but is length changing? No, length is not changing. So according to chain rule, again length can be taken out of the differentiation. And the third term, that is X, only B, L and X are the three terms that you have to differentiate, right? So the third term, which is X changing with time? I think so. Look at the rod is sliding with some velocity towards left, As the rod slides towards left, as the rod eventually slides towards left, I'm thinking the value of x is going to reduce as time passes, right? Because x is distance from A to D or from B to C. That is definitely going to decrease, right? That is definitely a change. So I can't bring x out of the differentiation and say that the differentiation of the whole thing is 0. No, x actually is changing. So differentiating the term or differentiating previous equation will give you this equation right here, that EMF is equal to minus BL dx by dt. And now we already know that dx by dt is rate of change of position. We know that what do we know? We know that dx by dt which is rate of change of position is velocity. We have learned already this in 11th, right? So rate of change of position is velocity. So I can replace this dx by dt with whatever velocity the rod is moving towards left. So therefore I can write the expression for EMF as, from the previous equation, minus B L into dx by dt. I can write it as V. Don't worry about the negative sign. Negative sign is only going to tell us the direction of induced EMF, about which we'll be discussing in the very next section. But for now, if you let's say are only interested in the magnitude of induced EMF, that induced EMF is simply B into L into V, and this is the expression for motional EMF. Here actually what happened was, the motion of the conductor in the region of magnetic field gave rise to EMF. Such an EMF is called motional EMF, and the expression is BLV. Notice the terms carefully. That V is the velocity with which the rod is moving, L is the length of the rod, and B is of course the magnetic field. And one crucial thing, alright, that's the expression for motional EMF. In the next section we'll be focusing on the direction of EMF, about that negative sign. This is just the magnitude. I'll just mention here that this is just the magnitude. We are not really worried about the direction, at least so far. We'll be worried about direction very soon, but for now let's say magnitude of induced EMF is so much. Alright, the next section is actually going to be one important discussion here, which is what if, notice one more thing, that the rod, the moving rod actually AB also is a conductor, okay, or the moving wire, you can say. The moving rod AB has to move or must move, perpendicular to the magnetic field. For example, I'll try to give a situation where there will be field, there will be a rod, and there will be motion. Just like in this case, there is field, there is rod, and there is motion. You got a non-zero EMF in this case. Good, great. It worked out really well for us. We had written a heading, and writing that heading and trying to discuss those things did not go waste. We did in fact get the expression for motional EMF. So far this seems like a success. All right. But can there be a case where there is magnetic field? Check. Motion, check. Rod of certain length L, check. But even in that case, you will not have induced EMF. Let's see if that can happen. And my explanation is going to be based on the sentence that I have written just before this, that the moving rod AB or whatever, oh my god, the moving rod is not actually AB, it is CD, my bad. The moving rod is actually CD. Alright, the moving rod has to move perpendicular to the magnetic field, otherwise you will not have EMF, is what I'm trying to say. Let's see how that works out. Let's say we will try to have a situation like this. Let's say you happen to have a situation like this, where the magnetic field lines are actually in this direction. this is the direction of magnetic field. Okay, so there is a region where the magnetic field lines are actually in this direction: magnetic field, magnetic field, magnetic field, magnetic field. And in this, now we have a rod, right? Let's say there is a U-shaped wire again, AB. Let's say this is that U-shaped wire, and let's say on this we have a rod which can slide over. So let's say we have this rod which can slide. Everything is same here, like I don't know, A, B, C, D, and let's say you're giving this rod a velocity of v in this direction. I'm not trying to discuss the direction of induced EMF. We're just trying to find if there will be induced EMF in this case. First of all, let's first cross check whether this situation satisfies this requirement or not. The requirement is that the rod AB or CD, whatever, the rod must be moving in a direction perpendicular to the magnetic field. Is that happening? I don't think so. Look at the velocity's direction. Velocity is directed like this in this situation, and magnetic field is actually in this direction. So magnetic field is towards right and velocity is towards left. They definitely are not perpendicular. In fact, they make a 180-degree angle between themselves. So they are not moving perpendicular to each other. So according to this statement, basically it should not give induced EMF. Let's see why. Let's see how. How come it is not going to give induced EMF? All right. To talk about induced EMF, what did we discuss that we need to have? We need to first of all have a flux, and then that flux should be changing with respect to time. All right, so let's try to write the expression for flux in this case, assuming of course this distance is x and this length is L. Everything I'm trying to keep it same except for the magnetic field's direction, which has changed, you know, to be in the direction opposite to velocity. All right, let's try to write the expression for flux in this case. Flux will be again B into area into cos theta. So B into area once again, if you see area of ABCD is once again L into x. All right, into cos theta. Now here let's focus on cos theta. All right, is B 0? No. Is L 0? No. Is x 0? I don't think so. See, x has its own value. Is cos theta 0? If now, you know, in order for me to prove my own statement that I have written a while ago, the only hope I have left right now is in cos theta. If cos theta becomes 0, then my statement over here in yellow color, that the rod has to move perpendicular to magnetic field, is true. Otherwise my statement, you know, it's going to sound foolish. But let's see. In this case, what about theta? If theta happens to be 90, let's please be 90, please be 90. Let's see. So if theta is, in this case, theta is basically, you know, angle between area vector and magnetic field vector, right? So this being your area, this right here being your area, if this is the area, if ABCD is the area vector is going to be perpendicular to this plane. And since ABCD lies on the screen, the area vector could either be perpendicular to the plane and outside, or be perpendicular to the plane and inside. This is the one of these two is actually the direction of area vector. And magnetic field actually is in this direction. See the red lines here. Magnetic field is in this direction, and area vector, like I said, could either be perpendicular to the screen and outside, or perpendicular to the screen and inside. One of these two is actually the direction of area. Either ways, the angle between magnetic field, which is to the right, and area, which could be inside the plane or outside the plane of the screen, are definitely perpendicular to each other. Therefore theta is 90 degree, and if theta is 90 degree, cos theta is 0, and if cos theta is 0, there is no flux to begin with. And if flux is 0, if flux is 0, then, you know, there's no point in differentiating 0, because anyway differentiation of a constant is going to be a constant again. I'm sorry, a differentiation of constant is going to be 0 again, right? So yeah, so there is no flux to begin with, so there is no question of rate of change of flux. So in this case clearly EMF is 0. So that establishes a strong point here. This yellow color line that we have written is actually very important, that the in case of motional EMF, having magnetic field and rod of certain length moving with certain velocity in the region of magnetic field is not enough, that the motion should be, if not exactly perpendicular, it happened to be perpendicular in this case, at least, okay, this statement is not 100% correct actually, but at least it should have a non-zero component in the perpendicular direction. The rod's velocity should have a non-zero component in the perpendicular direction to the magnetic field. Only then can you have motional EMF. If not, motional EMF will be 0. Alright, I hope the motional EMF part is clear. Tried my best here. Alright, so there goes motional EMF. The expression is BLV. In the next video actually we'll try to get the direction. Very interesting. Again, Lenz's law is going to kick in. Okay, so we'll try to find the direction of motional EMF in the next video. Alright, yeah, thank you.